In this lecture, we will introduce methods that can be used in order to include effects of electron correlation in electronic structure methods. In the last lecture, we discussed the Hartree-Fock method as being the most simple or most fundamental method that we could use within electronic structure theory. We saw here that the Hartree-Fock method was characterized by having each electron moving in the mean fields created by all the other electrons in the system. That is, in the Hartree-Fock method, we did not include any effects of direct electron-electron interaction, and this is what we will try to do here now. Now, this effect of direct electron-electron interaction, this is what gives rise to the correlation in our system, or the electronic correlation. Associated with this correlation is, of course, a correlation energy, and we define here the correlation energy as being equal to the exact energy for the system minus the Hartree-Fock energy, that is, the mean field energy. So the correlation energy here gives us a number which indicate how important effects of direct electron-electron interactions are in our system. We also saw in the last lecture that the Hartree-Fock method built it up on the assumption that we could represent the wave function as a single Slater determinant. What we will do here now is that we will introduce electron correlation through the use of so-called multi-determinantal wave functions, and to see that these can be used in order to introduce electronic correlation. Remember here that Hartree-Fock theory per definition gives us the best single determinant wave function, so in order to go beyond this we need to introduce more determinants in our wave function. The problem, of course, is now how can we actually derive more determinants? Well, if we go back here to the Hartree-Fock case illustrated here on the left in the figure here, then what we got out from a Hartree-Fock calculation of our system here was a set of orbitals, both occupied orbitals and unoccupied orbitals. What we can do now here is that in the expression for the wave function, or for the Slater determinant here, we can replace some of the occupied molecular orbitals by some of the unoccupied orbitals, and thereby we can get new Slater determinants which we can use in order to get an improved description of our total wave function. We can, for example, take one occupied electron here, and then we can promote this to one of the unoccupied molecular orbitals. This means that in the expression here for the Slater determinant, what we do is that we shift this one orbital here with this one orbital here, and then we have a new Slater determinant. This kind of Slater determinant is called an S-type Slater determinant, meaning that it is singly excited with respect to the Hartree-Fock case, that is, we move one electron. We can of course do this in different ways, as illustrated here. We can also excite two electrons, then we have D-type Slater determinants, means double excited determinants. We can excite three electrons, then we have T-types, triple excited Slater determinants, and we can excite four electrons, then we have quadruple excited Slater determinants. And we can continue by doing this until we don't have any more electrons in our system. That is, in the X-type Slater determinant, we would have promoted X electrons into the unoccupied molecular orbitals. So by doing this, we can construct a very, very large set of new determinants. Using these new determinants, we can now construct a new trial wave function to be used in the variational procedure. And this simply consists here of the Hartree-Fock determinant here with a given weight, then the sum over all the Slater determinants that we got by promoting a single electron, the sum over all the Slater determinants that we got by promoting two electrons, three electrons, and so on, until we do not have any more electrons in our system. If we include in this linear combination here of the Slater determinants all the possible excited Slater determinants, in addition of course here to the reference Hartree-Fock case, then we get the exact wave function for the system, meaning that we simply cannot do this any better. So we can see here that in order to improve upon the description of our wave function, we can start out here by the Hartree-Fock calculation using a small basis set, and we will get back to the meaning of basis set later on, and then we can increase the number of determinants to be included in the wave function. That is, we move up here. At some point we will reach the point where we cannot include more Slater determinants because we cannot generate more. This is called the full CI expansion or configuration interaction expansion, and this would be the best many electron wave function that we can actually produce. As we will talk about in the next video lecture, another way of actually getting the wave function more flexible or getting a better representation of the wave function is to enlarge the basis set that we use in order to expand our molecular orbitals, that is in the LCOW approximation. This is illustrated here by moving here to the right on this axis here, meaning that the exact solution to the Schrödinger equation would be found up in this corner here of the diagram. That is, using as large a basis set as possible together with a full CI expansion in the determinantal space. Another way of introducing the effects of electron correlation is through the use of density functional theory. And density functional theory is a method that has become extremely popular here during the last 30 years or so. What we do in density functional theory is that we shift the focus away from the wave function and instead focus on the electronic density. It turns out that there is a one-to-one connection between the energy and the density. That is, if we know the density here for our system, then we can actually calculate the energy based only on our knowledge of the density. The point is here, and this is the tricky point, that this functional here, f, which actually connects the density with the energy, is unknown. And this is all what density functional theory is about, simply to find as good as possible approximations for this functional which connects the density to the energy. If we reflect a bit here on the use of the density in our description of the system instead of using the wave function, then we can quickly see that if we can use the density in order to describe our system instead of the wave function, then this would represent a very large simplification, simply because, well, the density is a real function of only 3 variables, x, y, and z, while the wave function is actually a very complicated, usually, function of 3 n coordinates, x, y, z, for each electron. And in addition to this, we also have to take care of the spin variables in the wave function. So it seems here that the complexity can actually be reduced very much in focusing on the density instead of focusing on the wave function. And for this, we can use here the connection between the density and the energy. And again, the problem is that we really don't know how this f, the functional that contains the density with the energy, looks like. Now in 1965, Kohn and Schaum suggested to write up an energy expression for the energy based on the density, looking like this here. So what they did was to write the energy as a function of the density in terms of the kinetic energy of the electrons, the potential energy of the electrons interacting with the nuclei in our system, and then the electron-electron interaction described in this term here, using a Coulomb expression for the interaction between two charge distributions. Now what is neglected in this energy expression here is the correlation and the exchange energy. So what they did was to isolate this term here, which is usually the smallest one, namely the one containing the electron-electron exchange and correlation, into a given single term. Now further, what Kuhlmann-Schaum did was to reintroduce the concept of molecular orbitals and to use these molecular orbitals in order to calculate the electronic density. That is, they derived an expression for the density in terms of the molecular orbitals. And then by applying the variational principle to the DFT energy expression that I showed on the previous slide, we can derive an equation for the determination of, first of all, the orbitals in DFT, and then to use these orbitals in order to construct the density. So this is very much similar to what we do in Hartree-Fock theory. And here we also set up an equation that we could use in order to derive the expression for the orbitals that entered into the wave function. But unlike Hartree-Fock theory, what we do now is that we first calculate the orbitals and then the density. And in density functional theory, we now explicitly include the effect of both exchange and correlation. And this is different compared to Hartree-Fock theory. As in the case of Hartree-Fock theory, it turns out that this equation that will give us the expression for the molecular orbitals has to be solved iteratively using again some initial guesses for either the orbitals to begin with or the density to begin with. So still we need to proceed in an iterative way in order to determine the density or the orbitals of our system, exactly in the case as Hartree-Fock theory. What we gain by using this variational procedure here in the picture of DFT is that we explicitly introduce the effect of correlation, that is the term that exactly is missing within Hartree-Fock theory. We should remember here that it all relies on this approximate way of connecting the density to the energy, that is through this exchange correlation energy, which we actually do not know. So much research today within density functional theory is centered around developing functionals that can describe the exchange correlation energy in a well-balanced way. And we have different approximations that we can use for this. We will look a bit more into them in class. We have the so-called local density approximation, the gradient corrected approximation. The class of functionals that you will be using most will probably be the so-called hybrid models or approximations, which are listed down here, which basically consist of taking some of the exchange from a Hartree-Fock calculation and combining this with exchange and correlation calculated from DFT. Many functionals exist, and when you are to set up a calculation where you are to use DFT, then you will have to choose between different functionals. I have here given some expressions for some of the functionals that you can meet. In many cases, the functional called B3-lib here can be used. This is a well-tested and well-documented functional. For alternatives to this, well, we will talk more about this when we are to do the calculations at the computer exercises. If we briefly here look at the scaling of DFT with respect to the system size, the number of orbitals in the system, then it turns out to be around n to the power of 4. That is exactly the same scaling as we have in Hartree-Fock. So it roughly costs the same in terms of computer power to do a Hartree-Fock or a DFT calculation. But what we gain in doing the DFT calculation compared to the Hartree-Fock calculation is that we introduce the effect of electron correlation, and thereby we expect that the results that we will predict using the density functional calculation is of higher accuracy than the ones we would get from a Hartree-Fock calculation.